Hey guys, here we are for chapter 13, section 3, and today we're going to talk specifically about climate change. And not necessarily the core crux of environmental science, but what a lot of people tend to associate with it. So we're going to break it down today and look at it specifically. Your essential question: what are some of the most serious risks of global warming, which we also tend to refer to really as climate change? Climate change happens because of global warming. Something to think about as we move through today's topics. So first off, what is the greenhouse effect? The Earth itself is somewhat comparable to a greenhouse. The Earth's atmosphere acts like the glass. You get in a greenhouse. Well, maybe you don't have a greenhouse, but we've all got in cars. You know what it's like to get inside of a car in Florida in summer. You'll go, oh my goodness, it's so hot. The sunlight comes through the atmosphere, or just like in the car, into the car through the glass, and it warms up in the interior. That energy then radiates up from the surface. Some of it escapes, but the rest gets absorbed by the gases in the troposphere. Or in the case of the car, the energy comes in through the glass, warms up the car, and as it goes to escape, it's trapped in by the glass, right? Not all of it can escape back out, and it warms up inside the car. Well, the Earth acts the same way, with the troposphere largely capturing and re-radiating that heat. So it warms the air around us. And it's this process of warming the Earth's surface and the lower atmosphere, by and large the troposphere, that we call the greenhouse effect. Now, not every gas is a greenhouse gas. We talk about greenhouse gases. Only the ones that re-radiate infrared radiation. So, a greenhouse gas is any gas that absorbs and then re-radiates the radiation from the sun. So in other words, it captures the heat, it warms up, and then as it cools off, it releases that heat back out into the universe. Kind of like my coffee, right? You warm the water up and it holds the heat for a while, and then it slowly releases the heat back into the room. Not everything does that. When it comes to gases, some gases can absorb and store the heat and other gases don't. It's 4 biggies. It's 4 you need to know, and they're going to come up over and over again. And in proper order of the ones that do the most to the ones that do the least. Number 1, not carbon dioxide. Number 1, water vapor. Water vapor, just like my coffee cup. It holds heat and then it releases it. So water vapor, then carbon dioxide, then methane, and then nitrous oxide. So where do we get it? Water vapor is just coming from the water cycle, pretty simple. Carbon dioxide, anytime something is burned, we burn a tree, it releases carbon dioxide. You and I burn calories and we breathe out carbon dioxide. We burn fossil fuels, coal, oil, natural gas, it releases carbon dioxide. Anything is burned, it releases carbon dioxide. Methane, natural gas, it gets released up from the ground. Cow farts, if you will, it's a natural gas, CH4. Methane is an organic compound. So it is released from cows burping. When things rot, methane releases up. Once again, organic compound comes from living things. When they die, releases methane. And nitrous oxide. Largely nitrous oxide gets released when we burn oil and coal. Both of these release nitrous oxide. They're the big 4. Water vapor, carbon dioxide, methane, nitrous oxide. They are our 4 big ones and release most of the energy back up. Now, when it comes to measuring carbon dioxide, there's been a whole talk, we're releasing more and more carbon dioxide than there's ever been before. How do we know? Well, we've been measuring it. You and I aren't out there every day with a little carbon dioxide meter, but Charles Keeling was. In 1985, Charles Keeling installed an instrument in the top of Mauna Loa Observatory out in Hawaii. He wanted to start precisely measuring carbon dioxide in the air, but he wanted to get away from forests and cities. Well, carbon dioxide levels vary all the time. You go out into nature inside of the woods and you measure carbon dioxide levels and they're pretty low. You go into a city and you measure it and they might be pretty high. It also varies with the time of year, if you will. Well, his idea was this. He's out in Mauna Loa, the winds are blowing across from the Pacific. Once again, we have our prevailing winds, right? Well, they've been blowing for thousands of miles across the Pacific before they reach Mount Mauna Loa. So he theorizes that all of these carbon dioxides are going to mix and swirl before he get to measure him, and it would be a reasonable average of carbon dioxide levels on the Earth. It's a long way away from any particular city, any particular forest. Now, yeah, the island of Hawaii has a lot of forest, but the winds are blowing this way all the time, coming off of the Pacific. So it's not going to be getting the carbon dioxide readings from the island, only from the Pacific coast, prevailing winds again. So this was his idea. We'll mount it up there, we can measure it, and it should give us some sort of average of carbon dioxide on the planet. Instead of trying to go and measure it here, and collate all the data, it was a good idea, and he went after it, and he's been measuring ever since. Now, much of the carbon dioxide that gets released, whether we burn something, you and I are breathing, you name it, it occurs. It gets dissolved in the oxygen, just like oxygen dissolves in the ocean, so does carbon dioxide. And it also gets used by plants, right? So carbon dioxide is getting released and it settles back down to the ground. Plants are taking in some, the oxygen. The ocean is just absorbing a lot of it. Well, obviously, during spring and summer, plants are growing, right? The flowers pop out, the leaves come out, the things bud. So during spring and summer, the plants are growing and they're sucking up lots and lots of carbon dioxide. So during spring and summer, carbon dioxide levels tend to be lower. And then in the winter time, the leaves fall off, the grass dies, and all the carbon that was trapped in these escapes. As it dies, the carbon dioxide goes out, and they're not pulling carbon dioxide out of the air. So in the winter time, carbon dioxide levels tend to increase. In the same way, you go into a city where there's not as many plants, carbon dioxide levels are higher. You go out in the country, they're lower. In the spring and summer, they're lower. In the winter, fall, they're higher. So we have all of these numbers. And somebody can come along and say, oh, look, I just measured the carbon dioxide. It's really, really low. Well, it's springtime out in the countryside. Oh, I just measured it really high. And it's wintertime in a city. We needed to get something that could give us an idea of what was going on. Well, after a few years of measurement, it was obvious that the levels were undergoing some kind of changes other than these normal seasonal fluctuations. What we would expect is, wintertime highs, summertime lows, wintertime highs, summertime lows. We should just have a baseline average, right? Well, that's not what was happening. If you take a look at the chart back here, you can see the parts per million would rise and fall and rise and fall and rise and fall and rise, but overall we have a upward trend. Since 1958, the level of carbon dioxide in the atmosphere has increased over 20%. This is a very significant percentage over 50 years, and this is largely due to the increased burning of fossil fuels. We're burning coal, we're burning oil more than we ever have before, and we've now been burning it for a really long time, releasing more and more carbon dioxide, and it's more than the plants can scrub out on a daily basis. So if you look, it's hard to see on this, but there's a little light blue line. That's the highs and the lows, and the highs and the lows. The purple is just splitting the difference. You can't escape the aspect that between 58, and this is going up till 2010, it's gone from 315 parts per million up to 385 parts per million. That number is inescapable. It's a steady upward trend of carbon dioxide increasing in the years. Now, most scientists think that since greenhouse gases absorb and re-release radiation, that more greenhouse gases will result in increased global temperatures. This is a logical conclusion. It's a good hypothesis, right? Based on something we know, based on something we've seen, based on something we've read, or based on something that makes logical sense. Greenhouse gases capture, re-radiate heat. The more greenhouse gases we have in the air, the more heat they can capture and re-release, and our temperatures go up. A comparison of carbon dioxide in the atmosphere and global temperatures over the past 400,000 years. We don't have data in the terms of thermometers 400,000 years ago, but we have ice cores and samples. We can see what the carbon dioxide was a long time ago, and based on ice ages, other fossil evidence and remains, and geological, we get a lot of information. And we know the carbon dioxide levels have not been this high in the past, and they're increasing right now. Today, we are simply releasing more carbon dioxide than any other greenhouse gas. Once again, water vapor, you and I don't have much to do with it. It's just a water cycle. It's been unchanged for a long time. But carbon dioxide, we are burning more and more. Now it's a natural process, right? Forest fire releases carbon dioxide. A volcano erupts, it releases carbon dioxide. An animal breathes, it releases carbon dioxide. There's plenty of natural occurrences. But fossil fuels have been trapped in the earth for a really long time, millions of years. We are now pulling them out at a rate faster than we've ever done before, and we're burning them at a rate faster than we've ever done before, releasing more and more of the carbon dioxide. These are just hard facts that we have to accept. So the amount of greenhouse gases, including carbon dioxide, methane, nitrous oxide in the atmosphere is increasing. Fossil fuel burning releases them into the atmosphere. Global warming, as a statement, is just a gradual increase in the average global temperature. Average global temperature. And because the rise in temperature correlates to the rise in greenhouse gases, most scientists conclude that the greenhouse gases, along with other factors, have caused this increase in temperature. What we refer to as the greenhouse effect and global warming. More and more greenhouse gases, it warms up more and more. The chart back here right now is tracking from like 1895 to 2005. And this is just our global temperatures. Well, you know, from year to year, it rises, it falls. We have all kinds of things, right? The Pacific decadal cycle. We have volcano eruptions. We have the 11-year cycle of solar things. So all of this has to be taken into account. So from year to year, we get our, but once again, year to year, we see the averages sweeping upwards. This is just the hard and fast data that we're trying to get everybody to look at and pay attention to, because we don't want things to get out of control. We don't want to reach a tipping point, a point from which it's very difficult to recover. You know, I lean back in my stool, and for a while it's nice, and then all of a sudden, tipping points. We want to be careful of them. Now, temperatures are not necessarily rising at a constant rate or rising in everywhere in the planet. Certain places it's going to rise more, other places may wind up having a bit of a dip. We're talking about global overall averages. Just as with changes in carbon dioxide, short-term variations in temperatures have to get superimposed over these larger trends. So see, carbon dioxide is up and down, but overall it's going up. Same with our temperatures, up and down, but we get this upward trend, and this is what we're looking at. Now, because of all of these changes in patterns of precipitation, frequencies of fires, extreme weather events, and man, in this past year, we've seen a bunch. We've seen more forest fires. We had the most hurricanes ever on record this past year. So extreme weather events, more forest fires, these are actually occurring, and they're recorded as some of the most we've ever seen. So we tend to use the term, and we like to use the term, climate change as opposed to global warming. Global warming makes it think it's only going to get warmer everywhere. In other places, like, well, that'd be a good thing, right? If you're in Canada, a little bit warmer is good. But it's not just warming, it's change. Some areas are getting more rain than they used to, and other areas are getting less. Some areas we used to be able to grow plants, and now we can't grow them anymore. Spring's coming sooner in some places. It's climate change. It's a better reflection of the events that are actually occurring because of the overall global warming, because of the weather patterns, climate, ocean currents. All of these play a big effect in what happens to the climate in your specific area. Now, possible effects of climate change. Once again, let me address its possible effects. We don't know exactly what's going to happen where. We know what some overall trends will be, but it's hard to predict exactly what will happen. So, we expect to see changes in weather patterns, and we also expect to see rising sea levels. These are things we can pretty much count on. Now, the possible effects of a warmer Earth are not going to be the same everywhere, and countries are going to vary in their ability to respond and deal with the situations. Now, I'm going to run through a lot of various scenarios. Trying to get your notes from it, I only want you to get a couple of each one. It's a lot, and remember, these are possibilities. They are not absolute going to happen everywhere. They will definitively happen in some places, and they won't happen in others. But these are the kind of things that we can expect to see around the planet as we continue to go through climate change because of global warming. Sea levels have measured in a lot of places over the past 100 years, and they are rising, and they're going to continue to rise. One of the reasons is thermal expansion, all right? When something warms up, it expands. We see this all the time. We see it in a thermometer, right? It warms up and the thermometer rises, and it's just the thermal expansion that we're measuring. 71% of the world covered in water. That water warms up, it expands, and the water rises. Obviously, all of the ice, if the ice is stacked up, well, if the ice melts, the waters rise. So these are things we just know are occurring. This can cause local flooding around coastal areas. Beaches tend to get more erosion. The dunes wash out, we get more erosion. And then the salinity around bays and estuaries may increase. This can negatively affect things. Anytime we get salinity levels changing, whether it's getting more salty or less salty, it affects the wildlife. Any effect on the wildlife disrupts the food web, and we get all kinds of changes that can occur. If the Earth warms up significantly, we're only talking a couple of degrees, then the oceans will absorb more energy in the form of heat, which strengthens our hurricanes, may make hurricanes more intense, and actually cause more of them. Once again, this past year we had more hurricanes than we've ever had on record before. A lot of scientists are also concerned that climate change could cause a change in the ocean current patterns, such as the Gulf Stream could slow down. If it slows down, it delivers more warmth into this area, but less warmth somewhere else. So it could mean the eastern seaboard of the United States may wind up getting warmer. However, somewhere around England could wind up getting much colder. Once again, if these large weather patterns or circulation patterns change, it can be a huge effect. Human health problems. Obviously, the hotter it gets, we get human-related health deaths. Heat stroke, right? The hotter it gets, warmer, it causes problems for lots of people. We've already seen this happening for sure. Here in Florida, spring used to be March. It's not anymore. It's February. I guarantee you, you go out early February, by Valentine's Day, spring has sprung. It used to be very early March. Now it's mid-February. Climate change is part of it. So spring is coming sooner in a lot of areas. Well, this can affect allergy season. People have allergies longer period of times, have to start taking medicine sooner. Once again, it's in effect. Warmer temperatures encourage the spread of mosquitoes. So certain areas didn't have malaria and dengue fever, but now it's warmer and the mosquitoes move into those areas. So the areas that used to be too cold no longer are. Mosquitoes spread, just a reality of it. Agriculture. extreme weather events will tend to affect it. Extreme weather events, we're getting more rain here, but less rain here. Remember the El Nino, it affects 2/3 of the planet. So if some area is getting more rain, another area is getting less. So we can have droughts because of it, or more frequent in certain areas. Higher temperatures can actually result in decreased crop yields. Once again, it's change. Some areas it may actually be better, but other areas it's going to be worse. In any area that we already are growing crops and they go down, this is the concern, because we only have so much cropland out there. Once again, as a result, the demand for irrigation can increase. We're limited on our fresh water supplies now, and if we're having to try and move more water around, once again, change tends to be difficult, hard to deal with. Effects on plants. Temperature changes the range of plants. So some plants are going to start growing here where they didn't used to. Invasive species, they didn't used to be in that area, they swarm into it, we get a lot. Once again, it's a change. Change can be traumatic. Warmer climate can cause trees to colonize northward into cooler. And once again, they're just going to adapt to the new reality, and we're going to find plants here that we didn't used to find, and we're not going to find plants here that we used to find here. So in some areas, forests may shrink, in other areas, forests may grow. Increased use of forest fires are pretty much a given. Drier, and we see that. Animals are going to change migratory patterns. They may have to go farther north, not have to go as far south. Animals are going to shift where they go because they're following the food. They're not going to a location, they're just following food. Warmer surface waters are going to affect the phytoplankton, which then in turn affects the zooplankton, which affects the krill and everything coming around them. So we may see shifts in the food webs and the eating patterns. Warmer tropical waters can kill off algae. The algae nourish the corals. Coral reefs are incredibly sensitive. Too warm, too cold, they die. If they're not clear, they die. Warmer, once again, the weather patterns affect it. The more carbon dioxide that dissolves in the ocean, CO2 hits H2O, forms carbonic acid. Now, carbonic acid has always been forming in the ocean. It's just happening at levels we haven't seen before. And as the oceans get more and more acidic, it's causing an effect on the food chains, the food supply. So how do we reduce the risk? The best way to slow climate change that we are really aware of is weaning ourselves off of fossil fuels and more onto renewable sources. Solar, wind, water, geothermal. There's some other ideas we'll look at in another chapter, but these renewable sources, they're not burning fossil fuels, so it cuts down our carbon emissions, cuts down our methane, cuts down our nitrous oxides, reduces our gases in the atmosphere, reduces the overall temperature. But it's made very difficult because of economic, political, and social factors. We already have it in place to use fossil fuels. And switching from using a coal-fired plant to a natural gas-fired plant takes time and money. And switching from natural gas-fired plant to using primarily wind and solar is hard again. We've got to put the money into the solar, and it's a struggle. But it's what we're going through right now, and I think our future is really bright as we transition to use fewer fossil fuels and more renewable energy sources. Our renewable energy sources tend to be much cleaner, and I'm not talking just smog, the whole 9 yards. Conflict has already arisen over a lot of countries over future CO2 emissions. Everybody is trying to do what they can to reduce CO2 emissions, but of course, that doesn't happen with struggles because it takes politics getting involved, economies are disrupted by it. We've got to shift subsidies into coal into subsidies into wind and solar, and not everybody's happy with that, especially if you are making your money from coal, which a lot of people do. So it's a struggle, and it's not going to happen immediately. The Kyoto Protocol in 1990 was an international treaty that was an attempt to reduce greenhouse gases around the world. Many countries came in to do this. However, many countries ratified the treaty. They agreed to it, but not those most responsible. In other words, the United States. United States, China, some of the countries responsible for creating some of the most emissions did not sign the treaty because they saw it being neither politically nor economically friendly. So scientists, governments, organizations, businesses, and individuals are working very hard right now to reduce greenhouse gas emissions, and it comes down to all of us, you and me, doing our part, putting solar panels up on our roof, lobbying for our politicians to go to more clean, renewable energy sources, putting research into wind farms. Lots of ways it can be done, but it takes you and me at a grassroots level, encouraging everyone around us that this is the best thing for our future. And it'll be best for our future economically as well, but it's a struggle currently. Guys, that wraps it up for the chapter in climate change. Take care, and we'll see you next time.